welcome to Physics Teacher. In this live session, I'm going over an exam review for grade 12 university physics. Specifically, I'm going to be focusing on a whole bunch of multiple choice questions that I've used on previous tests and exams, as I know students really don't like multiple choice questions. So let's get some of those practice ins. Let me just make sure I have the chat. Open. Okay, I think the chat's working. If you're here, you can say hello in the chat, and then I'll know for sure. But I think it's okay. So let's get started with some multiple choice questions. All right, first question. 3 identical objects are thrown from the same height through a window at the same time. Object A is thrown horizontally at 4 meters per second. Object B is thrown horizontally at 8 meters per second. And object C is simply dropped. If air resistance is negligible, which object will reach the ground first? So we have to consider their vertical velocities. All of their vertical velocities start with a velocity of 0, right? Even if you're throwing something horizontally at 4 meters per second, 8 meters per second, or simply dropped, all the vertical velocities start at 0, so they're all going to hit the ground first, or at the same time. So no. B and C will land not first, they will land together, but with A. So all 3 will land at the same time. All right, next question, from question 9 to question 1. I pulled them from different tests and exams. 3 identical boats set out to cross a river that has a current. Boat A points directly across the river. Boat B points downstream some angle. And boat C points upstream at some angle. Which boat will arrive at the opposite side first? This is a fun question that I do with my class. If you have like a current through a river, one boat aims in this direction, one goes straight across, and one goes downstream. Now the question is not which one gets opposite to this, to that opposite point across the stream first, but just when does it get across the stream first? And this is very similar to the first problem because we have to think of components. Right? This vector is only a component across the river, where the other 2 vectors, A and C, have a component either upstream or downstream. But we don't care how far upstream or downstream they end up. So this boat is the one that will make it across first. And that was boat A, points directly across the river. So our answer is A. Okay. Anyone have any questions with either of those 2? Okay. I hope the chat is working. Let me just double check. Don't know how to type in the chat. Okay, well, let's move on. Next question. A car is traveling north when it enters a curve. It maintains a constant speed and leaves the curve traveling east. So we're starting off going north, and then we enter a curve, and now we are traveling east. The direction of the car's acceleration is. So there's a couple ways you can think of this. First, you can think of if you want to change your vector from north to east, you need to get rid of that north component. So you're going to need to accelerate south, and then you're going to add an east component. So you can think of it like that, and you can say southeast. Or you can think of this as circular motion, and during that circular motion, your acceleration is always directly radially inwards. So that would be in this direction here, which would be, again, southeast. Another way you can do it is you can say, well, acceleration is change in velocity, which would be final minus initial velocity, and negative initial, VI, is down. So if we were to add VF and negative VI, you get this vector, southeast. So there's 3 different ways you can view that problem, but our answer is going to be A. 16. A plane must fly to a destination that is southwest of its departure point. Okay, so we're going from here to somewhere over there, southwest. Because of the wind, it heads west, so it's only heading west. What direction is the wind blowing in? Okay, well, if it's only heading west, the wind has to bring it somewhat south. Now, we don't know if it's going to bring it somewhat southwest, or if it's going to bring it somewhat southeast, or perfectly south, because we don't have actual numbers to go off of, but the wind's going to have to be in some southerly direction. And there's only one option that has south in it at all, and that's A again. Got a lot of A's here. Does anyone have any questions there? Nope, no questions. All right. Let's move on. Number 18. Oh, I love number 18. 24 kilogram traffic light is suspended from the midpoint of a cable between 2 poles. The angle between the cable and the pole is 80 degrees at both poles. The net force acting on the traffic light has a value of. So I usually have a lot of students spending a lot of time working on this question, because we do questions like this in forces and equilibrium, and they also do it in their math course on calculus and vectors. Very similar questions. But you have to look at what the question is asking you. It is not asking for the tension in any of the cables. It wants to know the net force, and it tells you you're suspended. Therefore, the net force must be 0. No calculations required. So don't spend too much time on a question like that. Read it carefully. Reading a question slowly and carefully can save you time in the long run. So don't rush. Next question, number 21. Which of the following would be considered an inertial frame of reference? So an inertial frame of reference is a non-accelerating frame of reference. So we just need to look at all these examples and say, okay, which one is not accelerating? Okay, so you have a moving escalator. Oh, that's not accelerating. So there's our answer. Let's just double check the others. Car moving through a turn at a constant speed. Be careful. Even though it's constant speed, because it's going through a turn, its direction is changing, so that is acceleration. A free fall is when gravity is the only force that acts on you, so that's acceleration. A car pulling away as a traffic light turned green, that's acceleration, and it's certainly not all of the above. It's just A. Okay. Does anyone have any questions with those two? Nope. All right then. Let's move on. 17. The free body diagram of a car in a skid with its brakes locked is best represented by. Okay, lots of different options. One thing students love to add is, oh, someone said nope. Great, the chat works. Awesome. Thank you. I was curious if the chat would work or not, so that helps. Is best represented by. So a lot of students like to put an applied force on almost every free body diagram. but you don't necessarily need one. Even if you're moving forward, you can be moving forward with no force acting forward. Remember, your net force causes acceleration. So, in this case, you just have a car skidding. Of course, you're going to have gravity and the normal. All of them have gravity and normal except for D. So D is definitely not an option. Okay, and then all you have is with the brakes locked up. You're skidding, you have kinetic friction. That's all. And so that is A. A again. We've had a lot of A's. I guess if you're writing my exam and you don't know the answer, go with A. So far, that would work for you. All right, moving on. Number 19. An object is pushed horizontally at a constant velocity. Okay, constant velocity. That's important. Just underline that. What can correctly be said about the forces acting on the object? So, A, the forces acting forward is or are greater than the forces acting backwards. No. That would lead to an acceleration, and it's not constant. So, no. The sum of all forces have a value directed forward. Again, no, that would lead to an acceleration. Sum of all forces is 0. There we go. That's the one we want. You can check the next two, but I'm guessing they all have acceleration. The forces acting on the objects are unbalanced. Yep, so that would be acceleration. Newton's second law best summarizes the effect of the forces acting on the object. No, I wouldn't say so. That's net force equals mass times acceleration. Acceleration is 0. So I think inertia is a better one for this one. So no. All right. Any question there? Nope. All right. We got lots of multiple choice questions to go through. So let's continue. We're still in our first unit of dynamics. But this is going to be now circular motion. So a rock is tied to the end of a string and whirled around a circle that describes a vertical plane. So like this, going up and down. At which position is the tension in the string the least? All right, so it's either going to be the top or the bottom. Okay, it's not the ascending side or the descending side. So if we had a circle and it's going in this direction, it's not here and it's not here. Okay. Up at the top, we have both tension and gravity acting down. And at the bottom, we have gravity down and tension up. So if we're to maintain a certain centripetal acceleration, at the top, gravity is helping us. So tension doesn't need to be as big. But at the bottom, gravity is opposing us. And therefore, tension needs to be that much larger. So where's tension going to be the least? At the top. Okay. 22. The diagram below illustrates a car traveling with a constant speed around a curve in the road. So in this diagram, you're kind of seeing from the back of the car with a cross section of the curve there in the road. The curve is banked. Yes, the curve is banked. Which force represents the direction of the net force? Okay, so the direction of net force will be in the same direction as acceleration. And acceleration is always radially inwards. And if we have the car banking, if we imagine it on the screen going into the screen, and based on that bank coming around to the left, assuming the car doesn't slide down or up the incline, right there. That is the direction of centripetal acceleration. So our answer is B. All right. Any questions with those two? Nope. All right then. Let's do some from the next unit, energy and momentum. So question number 8. A car slows down as it descends a hill. Which of the following is true? You have to be careful with this one, because when we say a car slows down as it descends a hill, we like to think like you take a marble and you put it at the top of the hill. You like to think as it goes down the hill, it speeds up, but it's specifically saying it slows down. So So there's something else going on. Likely the car's braking, okay, as it descends a hill. So let's pick out the important information here. Thanks. And hi from Canada. That's awesome. All right, so gravitational potential energy decreases. Yes, that is true. It's descending a hill. B, kinetic energy increases. This is where it kind of tricks you, right? Because you think it's descending a hill, it's speeding up. But it clearly says it's slowing down. So take time, make sure you read and understand the question. Kinetic energy is decreasing. Heat is produced by friction. Yes, I'm going to assume yes, definitely. Heat is being produced by friction, especially if we're slowing down, because I'm going to assume we're braking. So yes. And these multiple choice questions are horrible because D and E are 2 of A, B, and C are correct, and all of A, B, and C are correct. In this case, only 2 of them. So our answer is D. Okay. Question number 20. When you catch a fast-moving baseball, your hand hurts less if you move it in the direction of the ball. True. Because, okay, this is impulse. Remember, impulse is force or net force times time equals our change in momentum. Okay, so in this case, your hand hurts less if you move it in the direction of the ball because you're increasing the time of that collision, decreasing the force. So let's look at which ones are true here. The ball changes momentum more slowly. Yes, we increase the time of the collision. The force applied is smaller. Yes, that is also a result of increasing the time of collision. You decrease the impulse required to stop the ball. No, absolutely not. Impulse is change in momentum. So if the ball is moving at a certain speed towards you and you catch it, it goes to 0. That's it. It went from a certain speed to 0. Doesn't matter whether or not you catch it immediately or you move in the direction of the ball, you're reducing its momentum to 0. So the impulse is going to be the same no matter how you catch it. So no. So again, 2 of the above are correct. Does anyone have any questions with those 2? Nope. All right. Next question. We got 2 13 questions, obviously from different tests. Question, the first 13, you want to ride a bicycle to the house shown above. Okay. Neglecting friction, at which point should you start in order to use the least amount of work to get there? So there's something else that we would have to neglect, and that is, well, if we started at E, without friction, we are not pedaling up the hill. So let's just assume we can still pedal up the hill even though we're neglecting friction. I think the point that wants to be made with that neglecting friction is as we go down the hill and up the hill, we're not losing any energy due to heat. Okay? So to do the least amount of work, you might think you would start at E, because that's very close. But A is right here. So if you started at A, gravitational would be converted to kinetic as you then go down the hill, and then converted back up to gravitational, bringing you right here. And then you only need to do that little bit of extra work. So in this case, it is going to be A, not E. Okay, and I have 2 versions of this question. The other version, I simply changed least to most, and it completely changes the question. If you want to do the most amount of work, you're going to start all the way down at the bottom at C. So read the question carefully. All right, the second number 13, this one. A 55 kilogram person carrying a 5 kilogram ball slides along a horizontal frictionless surface. That sounds like fun. He tosses the ball forward. So I'm assuming forward means that's the direction he's traveling. So he's moving forward and then he throws the ball ahead of him. What's going to happen? A, his path will not change. and he will slow down. Well, yes, that is true, right? If you throw it forward, you're not throwing it left or right. So no, your path is not going to change. And yes, he will slow down. So this could be, let's read the other ones. The ball will have a smaller angle. No angles. We're not throwing it any direction to the side. Okay, we can think of this almost as a one-dimensional question. C, his path and his speed do not change. No, definitely not. Momentum has to be conserved here. D, his path does not change, but he speeds up. Nope. That would be an interesting way of creating energy. No, definitely not going to happen. Energy also needs to be conserved. He will most likely stop moving forward. All right. There's a small possibility that he could stop moving forward. You would have to throw the ball pretty hard, though. I don't know if anybody has that amount of muscle to throw a 5-kilogram ball fast enough to stop moving forward and start moving backwards. Maybe if you definitely started at rest, then yeah, you would be moving backwards, but you're already moving forward. Doesn't tell you how fast you're moving forward, so you can't actually do those calculations. But the fact that it says most likely, I think that's where it's going to be wrong. And the best answer is going to be A, not E. Okay. Anyone have any questions here? Oh, thank you. They are good questions. My students don't agree, though. My students hate my multiple choice questions, but I quite like them. Thank you. Okay, let's move on. Question 15. A moving curling stone, A, collides head-on. That's important. We're not dealing with 2 dimensions here. It's a head-on collision with a stationary stone. That's important. The other one is at rest initially. B, both stones are of identical mass. That's also important. If friction is negligible during this linear, linear, that's another way of saying it's a head-on collision. But then it says elastic collision. That's important. We have a head-on elastic collision where one of the stones starts from rest. Okay, with an elastic collision, you have no loss in energy, so kinetic energy is conserved. And of course, momentum is also conserved. So there's only one possible outcome. Well, technically in the math, there's 2 possible outcomes. The first one is where stone A travels through stone B and keeps moving. But I think in our universe, that's very, very unlikely. So the other option is that stone A hits stone B, comes to rest, and stone B moves off with the same speed that stone A originally had. And let's look where that is. Stone A will slow down. Yeah, but it will come to a stop, so there's probably a better answer. After the collision, the momentum of stone B will be less than that of stone A. No, that's definitely a no. Both stones will come to rest. No. That's a big no. After the collision, the kinetic energy of stone B will be less than... No, definitely not. After the collision, stone A will have a speed. That's the perfect one we're looking for. Stone A comes to rest. Okay. For my students, we did a class very similar to this in our lesson on types of collisions where we did it with, I believe we did it with protons. Right? So if you wanted to look back at that, you can. All right, question 16. A car of constant mass doubles its speed while driving up a hill sloped at 45 degrees. Oh, I love this question. The factor by which its momentum changes is... Students like to overthink information that is given to them that is just not required. Right? I get students drawing triangles and doing SOHCAHTOA, trying to figure out what does this angle mean. No. Momentum is mass times velocity. So if your speed doubles, your momentum doubles. It doesn't matter if you're going up a hill, down a hill, or you're flying through the air in an airplane. If your speed doubles, your momentum doubles. So be careful with all the extra information. All right, any questions with those ones? Nope. All right. Next, we got springs and simple harmonic motion. Okay. If the period of vibration of a simple harmonic motion oscillator increases, so if you don't have the equations memorized, the period is 2 pi times the square root of the oscillator's mass divided by that spring or force constant K. So they're saying period increases. Okay. What are some possibilities for why that happens? A, the mass might have decreased. Is that possible? No. The mass is over here. They are directly related. If one increases, it's because the other increases. So if mass were to decrease, so would period. So no, this is no. Okay. The spring constant might have decreased. Yes. Okay, that's an inverse relationship. If K decreases, you can have period increase. So that's a possibility. So possible. The frequency also increases. Absolutely not. Period and frequency have an inverse relationship. If one increases, the other decreases. So that is a big no. Is it 2 of the above? No. Is it all of the above? No. Okay, so our answer is B. Okay, number 14. A spring-powered simple harmonic oscillator vibrates with a period of, okay, if the force constant of the spring is, the mass used is, okay, this is one of my rare multiple choice questions where it's just a problem that you have to solve on your calculator. Most of my multiple choice questions more test understanding, right? Because the problem solving of the exam comes later, right? If you wanted to see all those problem solving questions, I have a live that I did previously on just problem solving questions. So you can go check out my live sessions on my channel. But for this one is so easy it doesn't really deserve to be in the problem solving section because it really is just what I call plug and play. Right? We use this period equation up here. Get rid of the square root, so square everything. So we got t squared equals 4 pi squared times m over k. And then we are solving for the mass. Okay, so multiply by k. You got t squared k divided by 4 pi squared. Whoop, ran out of room there. 4 pi squared. And that equals m. So if you plug that into your calculator, you get 0.38, or rounded to 0.38 kilograms. Okay, an easy question. Anyone have any questions with those two? Don't worry. Lots more questions. You can see I'm only on slide 9 of 19. The last slide's awesome, by the way. Anyways, moving on, gravitational fields. Okay, gravitational fields. A planet has twice Earth's radius and twice Earth's mass. The value of G on this planet would be, okay, my students know I love proportionality questions, right? So you've got a universal gravitation, right? We have Fg equals G m1 m2 over r squared. Or if you're thinking of it as a proportionality, you have Fg is proportional to m1 m2 and inversely proportional to r squared. So if you were to double Earth's radius, so over here, and then double Earth's mass up here, whichever one you want to label as Earth's mass, what's the new value of G? Okay, this is Fg, but G is just, we can set this equal to m2G, right? So m2 just cancels. So we don't even care about m2. But don't put a 2 in the numerator and a 2 in the denominator and say, oh, nothing's really going to change. Something will change because the denominator is 2 squared. So we have 2 in the numerator, 2 squared in the denominator, which is 4. 2 over 4 is our new gravity is going to be half that of the Earth. Okay. Question 6. Question 6 looks like you might have to do some calculations. But remember, I like multiple choice questions that test understanding. So this one says Kepler's third law constant of proportionality for the sun is, okay, it's giving us some huge value. If Earth's radius of orbit is doubled, then CS would become. So if you remember Kepler's third law, it is proportional to, what is it, the cube of the radius and the inverse to the square of the period. It's a crazy equation, but the constant is the same for any object orbiting that object. So if you have the Earth, the constant will be the same for any satellite orbiting the Earth, the moon orbiting the Earth. Right? If you have the sun, it is the same for any object orbiting the sun, whether it's Mercury, Mars, Jupiter, Earth. Even if you took Earth and put it into a completely different orbit, which I hope never happens, the value of CS would not change. So our answer is just C, no calculations required. Okay. Anyone have any questions with those two? Nope. Okay. Next, looking at the diagram above, in which part of the orbit is the planet moving the fastest? Okay, this comes from also from Kepler's laws initially. You can also use Newton's laws to figure it out as well, but it's moving the fastest the closest you are to the sun. This is where it's moving its fastest, fast. This is where it's moving the slowest. This is why objects with very eccentric orbits, like comets that go all the way out to the Kuiper belt, we don't see them again, right, for hundreds of years. So us wouldn't, but our descendants would, because when they go all the way out to the Kuiper belt, they're moving very slowly. They're not going to come back for a very, very long time. So where is it moving fastest? A. And question 9. We have an orbiting satellite has a total energy of some number, then the binding energy is. So I know in this chapter there was a lot of new terms, but remember the binding energy is the absolute value of your total energy. Right? It's how much energy would need to be added to bring your total energy to 0. Okay, so in that case, change that negative to a positive, and we get B. There's our answer. Any questions? It's all right. All right. Electric and magnetic fields. Oh, I love electromagnetism. Probably one of my favorite units. I'm going to put my pen down because we're going to need our right hands for this one. The direction of the magnetic field B is from right to left as shown below. A proton, so proton has a positive charge, and so we're going to use our right hands, travels into and perpendicular to the plane of the page. Now there are different variants for the right hand rule. They'll all give you the same answer, but the one I use in my class goes like this. So you hold your hand like this. Okay. Your index finger, you're going to point in the direction of the magnetic field. Okay? I don't know if the picture you're seeing is inverted or not, but try it. Put your index finger in the direction of the magnetic field, which in this case is to the left. The proton, the speed of the proton, that's the thumb, and we're going to have this pointing into the page. So this is where things get difficult with your wrist. into the page or into the screen in this case. And then your middle finger points in the direction of the force. So in this case, it is up. Okay, so the direction of the force is going to be up. Okay, it's a good one to practice. Not too much though. Practice it too much, it starts to hurt your wrist. Okay. Oh, we're going to practice it again. So we have a conductor. It's located between the poles of a horseshoe magnet. Current flows in the direction indicated by the arrow. So that's supposed to represent coming out of the screen. And the magnetic field goes from north to south. So that's the direction of B. So in this case, again, right-hand rule, because we always talk about, typically we talk about conventional current. So that's the motion of positive charges. That's not what's actually happening, but it's a convention we use. So right-hand rule, index finger in the direction of, oh, this is going to be hard, in the direction of, in this case, to the right. And then your thumb is going to be the motion of the current. So that's coming out of the screen. So again, our middle finger is pointing up. We're going to have a force that is upwards on the conductor. It's a lot of A's. I did not do this on purpose, that most of my multiple choices are A. We'll see what the next few are. All right. The diagram below shows 2-point charges, B and C. So we can look at that and immediately. It doesn't say what they are, but we can see from the electric fields that this would be a positive charge, because field lines move outwards from positive charges and inwards to negative charges. So we already know a little bit of something there. Which of the following statements is true? Okay. A negative point charge placed at A, so if this were negative, will move towards the right. Yeah, okay. Another A. Let's check the other ones just in case there's a better answer. I don't think there's going to be a better answer because that's 100% correct. The charges are both no. The electric field is strongest near B. I wouldn't say it's the strongest because it looks like we have the same field density at C. So no, I wouldn't say it's the strongest. The charges on both B and C are no. A negative charge point at A will move to the left. No. Opposites attract. You can think of this in two ways. You can think of it as opposite attracts, and that the negative charge will be attracted to the positive charge. Or you can remember that negative charges always move in the opposite direction of the field lines they're in. And because this field line is extending, pointing to the left, a negative charge will move in that opposite direction to the right. That could be helpful if I didn't show you any of this and I just showed you these field lines. Right? But in this case, you can analyze it either way you like. Our answer is going to be A. Okay. Next, question 9. Which of the following statements are true about a magnetic force and field? So we got 3 statements, 1, 2, and 3. Number 1. A charged particle may travel through a magnetic field without experience a magnetic force. Yes, it can happen if the charged particle is moving parallel to the magnetic field. Okay, because if you remember the equation, Fm equals QVB sine theta, because it was a cross product, a geometric cross product between velocity and magnetic field. Yeah, if they're parallel, the cross product is 0. Right? Sine of 0 is 0. Right? So there is a way for a charged particle to move through a magnetic field without feeling a force. Number 2. The magnetic field of a current-carrying conductor points towards the conductor. No. If you have a conductor, let's say here's a conductor, and let's have a current going into the screen here. This is our other right-hand rule. So you take your thumb for your right hand, you put your thumb going into the screen, and your fingers show you the direction the magnetic field goes. So the magnetic field goes sort of around like this. It is not pointed inwards to the conductor. That's wrong. I hope one of these is right. Oh, wait. The first one was right. I said it was right. Why did I say no? That's a possibility. Number 3. If you increase the magnetic field, then you increase the kinetic energy of the charged particle. Ooh, this one's tricky. This is one I usually catch a lot of my students on. If you have a charged particle in a magnetic field, and assuming that it's not moving parallel to the field, so it's moving at some angle to the field, maybe even perpendicular to the field, it will feel a force. So you might think, well, if it feels a force, are you going to increase the kinetic energy? But that force is a centripetal force that always acts perpendicular to its motion. And so that force that always acts perpendicular to its motion only ever changes the direction of the particle and not its speed. Sorry. So the velocity does change, but not the speed. Because the speed doesn't change, you do not change the kinetic energy. So that's wrong. So only number 1 is right. So our answer is A. That's a really good question. Any questions with either of those two? Nope. Okay. Moving on then. What is the magnetic field at point Y halfway between the two conductors in the diagram below? Okay, so this is Ampere's law. But again, try to understand the question first before you start diving into trying to solve it with mathematics. So let's look at that right-hand rule I just showed you. So if we look at the top wire, this one, and you put your thumb to the right and you curl your fingers, at Y, the magnetic field is coming out of the screen. Right? So coming out of the screen like this. Okay. Now if you look at the bottom wire and you do that same right-hand rule, at Y, the magnetic field is going into the screen. And since these currents, since these wires have the same current I, and Y is halfway between them, meaning that it's at equal distance to each wire, the magnitude of the magnetic field of Y is the same but opposite directions. So the net field is actually just going to be 0. No calculations required. Okay. However, I could change the question and make one of the wires pointing in the opposite direction, and then you would have Ampere's law for a straight wire where you just have a multiple of 2 with that. Okay. Moving on. Ooh. Wave nature of light and modern physics. So let's do a couple of these questions. It's getting interesting now. 2 spaceships are heading to, well, it was always interesting. 2 spaceships are headed towards each other at a mutual speed of 0.999 c, where c is the speed of light. Why is it c? This is one of the ones I actually know why it's c. It stands for celeritas, which means swiftness. I just can't remember if that's Greek or Latin. It's usually one of the two. Both ships shine a laser beam at one another. Okay. How will each ship see the other light? A. Both ships will see the light traveling at twice the... No. This is special relativity. Einstein said that the speed of light is always c in all frames of reference. Actually, no, I don't think that was Einstein. It might have been Maxwell. Then Einstein used that along with Lorentz's mathematics to realize that you have things like time dilation and length contraction. But back to the point, the speed of light is always c in all frames of reference. So it's not going to be traveling at 2c for anybody. Neither ship will see any light. No, they should see it. There we go. Both ships will see the light traveling at c. I don't even need to read these two. They're wrong. Okay. Next, we have a length contraction question. What length will a vertical meter stick moving sideways at 0.99 c appear to be? So we have our equations with the Lorentz factor to figure out length contraction, but understand the question first. You have I don't have a meter stick on me, but let's pretend this pen is a meter stick. Okay, it's moving sideways. Length contraction occurs in the direction it's traveling in. So if this is a meter long, it will still appear to be a meter long. It's this that's going to contract, which would be the width of a ruler, not its length. So we're still going to measure the meter stick at 100 centimeters. It will not be less than that. I could change the question and say, what length will a vertical meter stick moving sideways at 0.99, or moving upwards at 0.99 c appear to be? And that would be a mathematical question. Okay? All right. We have a few more questions to go through, and they're going to get increasingly more interesting. At least I think so. These next two questions are on the photoelectric effect, what Einstein got the Nobel Prize for, actually. So 23. As the intensity of light increases in the photoelectric effect, the ejected electrons, A, have a greater velocity. No, because where would that energy come from? Remember, the energy of photons is related to their frequency, not their intensity. So you're not going to have that. You're not going to lose energy either. That doesn't make sense. Increase in number. Yes. Assuming the frequency is already high enough that you are overcoming that threshold frequency and you have ejected electrons. I'm assuming you have ejected electrons because it says what's happening to the ejected electrons. Your increase in intensity is going to increase in the number of those ejected electrons. But for question 7, says in the photoelectric effect, as the frequency of light shining on a piece of metal increases. Okay, so for increasing the frequency, we're increasing the energy. And if you've already provided enough energy to have those electrons ejected, then they are going to end up with more kinetic energy. Okay, so question 7 is A. Does anyone have any questions with that? Nope. Okay. We've got about 4 more questions. We've done a lot of multiple choice practice. These two you just kind of have to know. The strong nuclear force is carried by which mediating force? Okay, it's not photons. Photons carry the information for the electromagnetic force, not the strong nuclear force. Muons and pions aren't even mediating forces. They're not force particles. So they're a big no. The answer is going to be gluons. And bosons, well, I mean, that's a whole bunch of particles. It's not one specific particle. So no. Only the gluons carry the information for the strong nuclear force. Okay. Yes, D. Good. What is the quark pattern for a proton? Again, something you have to remember. So it's going to be, yes, awesome. Okay, up, up, down. Okay, if you can't remember it's up, up, down, you have to remember something. If you can't remember it's up, up, down, you could remember that an up quark has a charge, a fractional charge of 2/3, and a down quark has -1/3. And then you know that a proton has 3 of them. And you're going to end up with a charge of +1. So you can figure that out, that it's up, up, down. Or you can just remember it. For those of you that don't know, if we put a line above it, that means it's an antiparticle. And protons are not made of antiparticles. Okay? And it's also not A, right? Protons are made up of 3 quarks because they need to be color neutral. Up, down, down, that's our neutron. And I could change this question and say, what's the quark pattern for a neutron? In which case it would have been C. All right, we've reached the last slide. I think we've done like 36 multiple choice questions, but these are fun. Number 19 is again about the strong nuclear force. This says the electromagnetic force pulls opposite charges together, yes, and pushes like charges apart. Yes, opposites attract, like charges repel. The strong force, however, is different from the electromagnetic force in that the strong force is only attractive. Yes. And it has how many types of charge? It has 3 types of charge. We call this color charge. And so we have our red, blue, and green color charges. So we have 3 types, not 2. So these are automatically off the table. Okay. Now, the interesting thing with the strong nuclear force, unlike gravity, the further apart you get, the stronger it becomes. So a lot of the times when you draw like a proton, you probably see it drawn with like springs, because a spring is a good way to visualize it, because the more you pull apart springs, the stronger they pull back together. So it's a good way to visualize it. So we got 3 types of charge and gets stronger with distance. Okay, our answer is B. Okay, moving on to our last question. So light is polarized at -45 degrees, so like this. That can be written as a superposition. So if we're looking at polarization as either being horizontally polarized or vertically polarized, then something that is polarized at, say, an angle would be a superposition of those horizontal and vertical polarizations. Specifically, this one would be a superposition of horizontal and negative vertical. Okay, so it's not these two. Okay, horizontal and negative vertical, horizontal and negative vertical. It's not going to be this one. So it is it either a half or is it 1/√2? So that's our amplitude. And when we're dealing with superposition, we're dealing with probabilities. And the probability is the square of the amplitude. Now, if you're at -45 degrees, that's perfectly in between 0 and 90, or 0 and -90. So you have an equal probability. It's a 50-50. That doesn't mean it's 1/2, right? So I said the probability is the square of the amplitude. So if we took 1/√2 and squared it, you'd end up with 0.5 or 50%. So our answer is D. That last one is a fun one that I do with my class, but you may not have that one in your class. But I hope all those multiple choice questions were good practice. This video will be available on my page to go look at it anytime you like. I also did a previous live session where I go over all different problem-solving questions you could see on your grade 12 physics exam. So you can take a look at that one as well. All right. Any last questions before I go? No? All right then.